Welcome back, everyone, to this lecture discussion on classification performance metrics. We just saw how a model can predict the classes based off some input features. What we don't know yet is how to actually measure the performance of these predictions. And in part 1, we'll begin by discussing the confusion matrix basics. You've probably heard of terms already, such as a false positive or false negative, as well as metrics like accuracy. But what do these terms actually mean mathematically? Well, let's imagine that we've developed a test or a model to detect the presence of a virus infection in a person, based off some biological feature, maybe for example a saliva sample. And we could treat this as a logistic regression or machine learning model, predicting one of two possible outcomes. We'll predict a 0 if they're not infected, that is, they're testing negative according to our model, or we'll predict 1, predicting that they are infected, saying they test positive. Keep in mind, in the real world, it's unlikely our model will perform perfectly. That means there's actually 4 possible outcomes. The first 2 is that an infected person takes our tests and they test positive, meaning they do have the virus. The second possibility is that a healthy person takes the test and they test negative, predicting that they do not have the virus. Note that these are the outcomes we actually want, correct predictions, but it's unlikely our test is perfect in the real world, meaning there's 2 other possibilities. We could accidentally or incorrectly say an infected person tests negative, or our model could incorrectly say that a healthy person tests positive, essentially saying, for each of these, that an infected person doesn't have the virus, which is not true, or a healthy person does have the virus, which is also not true. So with these 4 possibilities, what we can do is build out a matrix. So there's many error metrics we can calculate, and this all stems from visualizing these 4 possibilities. Let's begin by understanding how a confusion matrix is built. Along the columns, I'm going to say these are the actual results of the person. And keep in mind, this is all based on training data where I actually have the historical label information. So I actually know the true values for the person's infection, whether or not they are infected. So essentially, we're developing a test and we're measuring how accurate or the performance metrics of this test. And I can really only do those measurements if I know the correct answer beforehand. So I already have the actual information if the person is infected with the virus or if they're healthy. Then I'm going to take the results of my actual test, essentially what I predicted. Did I predict that person was infected with the virus, or did I predict that person was healthy? So if the person is actually infected and I predict they were infected, that is known as a true positive. And keep in mind, this doesn't need to be just for something like a medical test of a viral infection. We're essentially just doing this for any binary classification problem where I have a relevant label I'm searching for and a not relevant label, such as infected versus healthy. So if they're actually infected and I predict they're infected, we label this as a true positive because I correctly reported them as positive presence for the label I was looking for, that is a 1. However, let's imagine they test negative and they're actually healthy. So if they're actually healthy and I predict that they're healthy, that is that I correctly labeled them as 0, essentially no presence of the label I was looking for, and that is known as a true negative. These are the 2 results that we essentially want to maximize. Now let's imagine that the person is healthy, but I predicted them as infected. This is known as a false positive because I'm incorrectly labeling this person as positively infected when they were actually healthy. And then the last one is if a person was actually infected, but I predicted them as being healthy, that is a false negative. Now if these 4 metrics, true positive, and false negative, true negative, I can calculate many different ratios in order to come up with different performance metrics. So let's imagine a test group of 100 people. 5 are infected and 95 are healthy. And what I do is I test all of these patients and then come up with some results. So we tested all of them and we have these results. Recall that I will already know who's actually infected and who's not infected. And another thing to keep in mind is technically only 5% of my entire population that I was testing on happened to be infected. And so with these results, what we can do is begin to calculate some error metrics. The first one we're going to talk about is accuracy. And let's begin by discussing what is accuracy. You'll often hear things like, this test is 99% accurate. But what does that mean mathematically? Accuracy is essentially answering the question, how often is the model correct? And this is calculated by adding up the number of true positives and true negatives and dividing by the total. Which means I have 4 true positives and 93 true negatives, which essentially means 97 of those people that I tested on, I actually predicted correctly. So this means my test is 97% accurate. Now, the obvious next question is this actually a good value for accuracy? And this is where the accuracy paradox comes into play. You may have heard that many tests just tout how accurate they are, but this could lead to a paradox in situations where you have an imbalanced label. In order to understand the accuracy paradox better, let's imagine we always report back healthy. So I have this very simple model that regardless if this person has the virus or is healthy, I just give them a slip that says, I predict you're healthy. What would our model look like then? Well, in this case, you'll notice that my prediction for the infected row becomes straight zeros because we're always going to report back healthy. And so now, you'll notice that if I were to ask the question of accuracy, how often the model is correct, I still get quite a high accuracy because while I have 0 true positives, I still have now 95 true negatives, which means this test, even though it always reports back healthy, is actually 95% accurate. So we have this 95% accuracy for a model that is clearly wrong. It's always returning healthy regardless of the actual person being tested. Now you may be thinking in the example we just showed, the numbers were completely made up and arbitrary. We just happened to get a good accuracy in this made up case for a ridiculous model that always reports back healthy, and that real world data would actually reflect poor accuracy. However, this is not the case, and imbalanced classes are actually much more prevalent in the real world than one would think, and that's why we have this accuracy paradox. So, to clarify this accuracy paradox, it really has to do with the fact that in the real world, you often have data sets that have imbalanced classes, and any classifier dealing with imbalanced classes has to confront the issue of the accuracy paradox. Imbalanced classes will always result in a distorted accuracy reflecting better performance than what is truly warranted. Imbalanced classes are often found in real-world datasets in tons of different fields, especially when we talk about fields such as medical conditions. Often, certain medical conditions only affect small portions of the population, or also things like fraud. In general, fraud is actually not that common when you take into account the entire aggregate of everything that's going on. For example, if you were to take the ratio of fraudulent credit card transactions versus legitimate credit card transactions, fraud is actually a very small percentage of every single credit card transaction that is happening, which means if we were to create a model to try to detect this fraud, accuracy alone is probably not a good metric. So the main thing to note here is that if a class in this real-world dataset is only a small percentage, that is something like n%, 1%, 2%, or 3%, or something small like that, then a classifier that always predicts the majority class, that is the much larger representation percentage, it's always going to have an accuracy of something like 1 minus n. So in our previous example, if you recall, we only had 5 infected people versus 95 healthy people, which allowed us to actually get 95% accuracy even if we reported anyone as healthy. And again, many real-world datasets have imbalanced classes. So for example, if only 3% of credit card transactions are fraudulent, and we have a model that tries to detect fraud, but accidentally always predicts every transaction as legitimate, then we would just say 1 minus 0.03, or 3%, and that would actually lead our model to say that it's 97% accurate at figuring out whether something is fraudulent or legitimate. So this means we shouldn't solely rely on accuracy as a metric, especially if we're dealing with imbalanced classes. And this is where other performance metrics come into play, such as precision, recall, and F1 score. Let's explore these other metrics in more detail in the next lecture.